So sometimes the literature is wrong, and Gilad is going to tell us about something we thought we had, but we didn't. Call set agreement in actual constant time.
Thank you. I'm actually not going to go into the controversy too much. I'm going to tell you what we did. This is a joint work by Itai Abraham, Gilad Asharov, Varpita Patra, and myself. All right, so we're going to start off with a network and adversary model. Our network is fully connected, has end parties, and we assume you have kind of direct links and they're secure and authenticated. We're going to work in asynchrony. So I think a lot of you are probably used to thinking in synchrony. You have rounds, you start at the beginning of the round, you send a message, and it arrives, and you start the next round, and you kind of do this round by round. And in asynchrony, you just don't assume that. You only assume that messages eventually arrive, but you don't know how long it'll take, you don't have any known time bound, just that they arrive. And we also let the adversary choose the delay. Now, in a theoretical standpoint, that's nice. It allows us to do stuff in a more general model, stronger adversary, and we prefer doing that if we can. I think it's also interesting from a practical standpoint. If you think about instantiating a synchronous protocol, there's often an issue of choosing how long to wait. You often wait enough for the round to pass by. And then you need to set some delta and to wait a delta time. And if you don't wait enough, your protocol stops being secure, right? So you wait, maybe a little more, and all that waiting is just slow, right? We don't want to do that. So conceptually, we prefer working at network speed, just not having deltas anywhere and just working as fast as we can. And this forces us to do that. Now, an inherent challenge here is now how long do we wait, right? At some point we need to go to the next step, and usually we do this by round, so we need some logical kind of reason to do that as opposed to a time-based reason. Oh. All right, we're going to work with an adaptive malicious adversary. Malicious just means it can deviate from the protocol however it wants, and adaptive means that it can corrupt parties at any point in time throughout the protocol. It doesn't have to do it in the beginning. We're going to work with optimal resilience. That's n greater than 3t. T is the number of faulty parties in consensus-related stuff, and n greater than 4t in AVSS. And finally, we want perfect security, and we analyze this work in the UC framework. All right, so we already heard some talks about MPC. I'm going to talk a little bit more about asynchronous MPC. Kind of very informally, we want to construct protocols that have the following behavior. Each party has an input. It provides this input to the network somehow, and then everybody receives a function of those inputs, of all those inputs as output. And ideally, we definitely want parties to not learn anything else. Now, this is a very nice kind of picture. In asynchrony, with an adversary, we have a following kind of issue. The adversary can do pretty much the most dangerous thing it can do, and that's nothing. It can just not talk. And if you don't talk, now you need to choose. Do you proceed or not? That's kind of related to what I said before. So here, you could kind of maybe hope that the last party is honest and just we haven't heard from it yet, and then we'd wait. But if we do so, we might wait forever, right? Because if it's dishonest and didn't say anything, now we'll get stuck. So we don't want to do that. Kind of intuitively, we have to start processing stuff after receiving 3 inputs. Or rather, having these inputs provided. And now the second most dangerous thing the adversary can do is say anything. And if it says anything, now we need to kind of decide which inputs to use. And there's an issue here, since we're asynchronous, we might learn these things at different times. So the first party might kind of see parties 1, 2, and 3 input values, the second party might see 1, 2, and 4, and the third might see 1, 3, and 4. And now we don't want to end up computing the function on different sets of inputs, right? So in order to solve this issue, we have agreement on a core set. Agreement on a core set essentially solves this exact task, which parties inputted stuff. The state of the art is work from the 90s. A work by Michael Beno, Ran Canetti, and Oded Goldreich solved this task in perfect synchrony. Sorry, in perfect security. And a year later, a work by Michael Beno, Boaz Kelmer, and Tal Rabin solved the same thing with statistical security. Both of these works kind of solve each, or look at each one of the parties separately and agree bit by bit whether to include these parties or not. The more efficient of the two works requires n to the 7th log n expected bits and a logarithmic number of expected rounds. And when I say expected bits, I mean the total communication network. Our work doesn't do this bit-by-bit agreement. We just think of the set as a single value, as a large value. And instead, the thing we do is we construct a single multi-valued agreement protocol, and using that, we solve the task. Our work requires n to the 4th log n bits and a constant number of expected rounds. So just doing a little bit of math, not too complicated. This is shaving a cubic factor in the number of bits and a logarithmic factor in the round complexity. All right, so this is one prong of improving MPC. The second prong is improving VSS. We've already seen some works that use VSS in MPC. In a VSS protocol, we already saw that a little bit. We have two phases, a share phase and a reconstruct phase. The share phase has a dealer. The dealer has a bunch of secrets. I'm going to look at a packed variant, by the way. We already heard that word earlier. So it has a bunch of secrets. I'm going to think usually of a linear number of secrets. And then it's going to provide these secrets in some secret fashion. They're called secrets. And if it does so, everybody's going to see that that has happened. We'll have a done signal. And importantly, they won't hear anything else. You just will hear that secrets have been provided. It's important to note that if the dealer chooses to provide something, it could be malicious, it could not provide anything, but if it does provide something, it's committed. It's binded to these values and it can't change its mind. All right, and then the second phase is a reconstruction phase, and in reconstruction, each party can choose to reconstruct a given secret, and then they do so, they receive the secrets, and output them. And again, these are the same secrets binded in the earlier phase. And importantly, you don't learn anything about any of the other secrets. You only learn the specific secret you reconstructed. You can do that separately. All right, so the improvements we get here. The state of the art currently is a work by Choudhury and Patra from a couple years ago. And they have into the 4th log n bits for sharing a linear number of secrets. And our work improves that to enter the 3rd for the same number of secrets. And we have all kinds of efficient reconstruction tricks. Actually, both works can do this. You can reconstruct sums of secrets or batches of secrets, and this allows you to do the reconstruction efficiently. If you can do each reconstruction normally costs quadratic costs, so you don't want to do that too many times, and you can do efficient tricks. All right. So taking these two improvements, we're going to look at MPC throughout the ages, or asynchronous MPC, sorry. The first of these works is BCG, we already talked about it. It has C times n to the 6th cost, where C is the number of multiplications plus the cost of a single ACS, and the tilde is hiding a bunch of stuff. I'm going to actually show you an actual number later. And then we kind of go down to n to the 5th, and cubed, and squared, and finally C times n. All of these with the cost of a single ACS. And all of these works have the round complexity is D, where D is the depth, plus log n rounds, an expectation. The final work is a work by Itai, Gilad, Arpita, and Shravani Patil. So kind of recapping, the current state of the art, or up until this work, is this work APP24, and their actual full cost without hiding any factors is Cn plus Dn squared plus n to the 7th, all times log n, plus D times, and the round complexity of D plus log n. Now, our work reduces the n to the 7th down to n to the 4th, and the log n down to a constant. And that kind of relates to what Pierre said. Up until now, we thought we had a way to do this constantly, and we actually didn't up until we did that. Now, it's important to note that this is not only by using the ACS. It's actually, the AVSS also allows for the improvement in communication complexity. All right. Peeking a little bit at the state-of-the-art synchronous MPC, also by APP, but a year before that, their complexity is exactly the same. So at least for now, the state-of-the-art for synchronous and asynchronous MPC, with guaranteed delivery and all kinds of good stuff, is the same. And kind of as a meta question, I think it's interesting to note that this is the same, and is this always the case? I doubt it, but where can we make these things match? I would like every asynchronous protocol to be as efficient as every synchronous protocol. All right, so kind of diving into the consensus specifically, consensus is a big part of this work. There's a lot of words here, but in essence, this is a multi-valued consensus protocol. It's based on the no-waiting hot stuff protocol from a year ago by Itai, myself, and our 3 excellent co-authors, Filip Jovanovic, Mary Mahler, and Sarah Michaeljohn. This is a cryptographic protocol. So we adapt cryptographic techniques to information-theoretic techniques. And kind of in structure, maybe it's a little hard to see, we have an ACS protocol. The ACS calls the multi-valued agreement once. The multi-valued agreement calls a leader election kind of protocol, and inside we use our VSS. A technical note that I think is interesting is that our consensus uses a notion of external validity that's kind of new and kind of old. For those not in the know, external validity is kind of a function that allows you to check whether an output makes sense in some way. So here in this context, makes sense would be something like, this is a set of enough parties that actually input values into the MPC, right? And that's what makes sense would mean in this case. And we only want to output values that do make sense. And this is usually verified cryptographically. And since we're information theoretic, we don't want to do that, right? So instead of doing that, we kind of think of a parallel, an information theoretic parallel of that notion. And since it's kind of event-based and asynchronous, you have all kinds of little things that go into the definition there, it's a little intricate. And I think it's interesting to think about. This is very similar to BKR's dynamic predicate with a little bit more specification. So in that sense, it's also old. Like it's not entirely new, but the exact specifications, I think, weren't always fully defined. All right. It's important to note here that this entire protocol, with the exception of the VSS, is secure for n greater than 3t, so optimally resilient. And we do know how to construct VSSs that are resilient for n greater than 3t that are statistical. We do know how to construct leader election protocols. So in essence, this entire protocol could be optimally resilient. We don't need that. We're thinking of the n greater than 4t setting, and then we have a more efficient AVSS. And I think those that can see from far away can tell that the communication bottleneck is actually at the AVSS. That's the most expensive part here. Everything here is cubic except for the n AVSSs, and doing n of those is a quartic. It's n to the 4th. So improving that will also improve the communication complexity of this entire protocol. All right. Thank you very much.